Um, but of course, I'll also keep an eye on the chat. So you can also ask questions on the chat, but just feel free to. Okay, so let's begin. We'll be recording this, so just to let everyone know, and we'll be putting up the recording on the IMSC Algebraic Combinatorics, our website. So welcome everybody to the IMSC Algebraic Combinatorics seminar. It's a great pleasure today to have Mike Zabrocki from York University, Toronto. And he's going to be talking about symmetric group characters as symmetric functions. Over to you, Mike.
Thanks a lot. So if you ask a question in the chat, please flag me to make sure I'm aware that it's there. So
yeah, I'll try and keep an eye on that.
Okay.
And yeah, maybe people should mute their mics unless they're asking questions. Yeah.
Okay. Well, thank you. So this talk lies in the combinatorial representation theory, and really where I'm coming from is a perspective that I want to study representation theory, but from a very, very detailed point of view. I want to be able to compute. I want to be able to compute as quickly as possible. And I want to understand my representations with as much detail as possible. So down to the very basis. So I may know the dimension is indexed by a combinatorial set of objects. The dimensions are equal to the number of a combinatorial set of objects. And I want to know so far down is to try and understand what is a basis that is indexed by that combinatorial set of objects. And my tools that I'm using are those of symmetric functions, where we understand really well the certain collections of bases that help us decode what's going on in the representation theory. So the representation theory is very difficult to compute, and we can reduce that problem by looking solely at its characters, and those are what's going on in the symmetric functions. And then all along, we're looking at combinatorics, using that as our guide for how we're going to understand this, the representation theory. So I'm going to start off by giving a basis of knowledge on representation theory to where we're starting from, and that is, so I'm getting so many beeps in my ear. Are they all coming through? No?
Yes, unfortunately.
I can't tell where they're coming from because they shouldn't be on my computer. Sorry, it could be. Oh no. All of those are coming through. My campus was hacked on Friday, and they just restored email, and that's why I'm getting thousands of beeps. Hopefully those will stop. They're all happening now. Let me try and shut down the mail.
It isn't too loud or anything.
Oh, but I thought it was coming from somewhere else, and I said it can't be coming from mine because I haven't been getting email for 5 days. No, I could get all of my email from the last 5 days at the same time. Okay, so start off that I want to start with a background knowledge of representation theory, and that's kind of hard to do because representation theory itself is a very, very hard subject. The idea is that we're trying to describe the maps from a group to the general linear group. And that's an infinite space. That's an infinite set. But the maps themselves do have a lot of structure to them because groups have a lot of structure to them. And how they can be understood was laid down at the beginning of the 19th century. So this was by mathematicians, mainly in Germany and in the UK. And they were trying to understand the structure of groups and the structure of group representations. And so the mathematics that I'm starting from was all started end of 19th century, beginning of 20th century. And the names that of the results are all associated to mathematicians that were based in Europe, and they they kind of discovered how the mechanics of representation theory works. But I'm interested in attacking some of the problems that are still left open. So the first thing that I want to highlight is that all of the general linear group and symmetric group representations can be broken down into irreducible representations. So although we're describing all of the maps from a group to the general linear group, either from the symmetric group to the general linear group or from the general linear group to the general linear group, that these representations can be broken down into irreducible ones. And so really what we want to understand are the mechanics of how the irreducible representations work. The irreducible representations of the general linear group and the symmetric group are closely related. And that is, I'm vaguely referring to this idea of Schur-Weil duality. And so I'll give a few more details of what that is, but it's a concept that was in Schur's thesis in 1905. And then it was popularized by Hermann Weyl when he wrote a book on the representation theory of classical groups. And it says that the general linear group representations and the symmetric group representations are very closely related, and I'll make that more precise. Irreducible representations of the general linear group and the symmetric group are indexed by partitions. So I'll tell you what a partition is in a minute, but and the maps that we're trying to describe, the very representations that we're trying to get our hands on, are characterized by a small number of values called characters. So if you know the characters of a representation, then essentially you know the representation itself up to isomorphism. And that's all that we care to understand here, is just to understand what representations we're trying to get at by how they decompose into irreducible representations, and just knowing the characters is sufficient. And so the takeaway message from this slide is I want to know irreducible representations. Those irreducible representations are indexed by partitions, and it suffices to know the characters. So the combinatorics I'm going to need are the idea of a partition. A partition is a weakly decreasing sequence of integers, positive integers, that add up to a number n. So a partition of n is a weakly decreasing sequence of integers that adds up to n. I'm going to represent partitions by, these are called Young diagrams, or Farrer's diagrams. The partition 10, 7, 7, 5, 2, 1, 1 has 10 boxes in the first row, 7 boxes in the second row, 7 boxes in the third row, 5 boxes in the fourth row, 2 boxes, 1 box, 1 box. And I'm going to denote that, so the sum of these integers is 33. So I'm going to denote that this is a partition of 33 by saying lambda, and I'm putting the symbol, it's a v dash 33. And so now remember that irreducible representations are indexed by partitions. So the other combinatorial object that I'm going to look at, I'm going to need for this talk is column strict tableau. And a column strict tableau is you take a partition, a diagram for a partition, and you fill the boxes of that diagram for the partition with the integers 1 through n. And you're allowed to repeat. Now the cells then have these labels with 1 through n in them, and the labels of those cells must weakly increase as you move along the rows. So as I move along the rows, they weakly increase, and as I move along the columns, they strictly increase. And I have a given column strict tableau has both a shape given by which partition it is that I'm filling, and it has a content by telling me how many ones there are, how many twos there are, how many threes there are, how many fours there are, how many fives there are, how many sixes there are. And that content itself is a vector. This one says there are 4 ones, 3 twos, 4 threes, 0 fours, 3 fives, and 1 6. And a column strict tableau is called standard if the content is 1 to the n. So for where n is the size of the partition. So the other 3 corners, I have 3 corners of my combinatorial representation theory. I had combinatorics on one side, I had symmetric functions on the other side, and at the top I had representation theory. So the other base of what combinatorial representation theory is about is this Hopf algebra of symmetric functions. So symmetric functions are starting, I'm starting with the idea of a symmetric polynomial, and then I'm getting rid of the variables. So because every symmetric polynomial can be written as a polynomial in my power sum generators, then I have that the elements PA1, PA2, PAR are monomials in my power sum elements, and they must span my symmetric polynomials. And then, so I can take, because multiplication is commutative, I can reorder the variables so that they occur in weakly decreasing order. And so basis for the Hopf algebra of symmetric functions is P mu, where mu1 is greater than or equal to mu2 is greater than or equal to mu3, and so on. So this is P mu, where mu is indexed by a partition, forms a basis. And my Hopf algebra of symmetric functions, I can describe it completely on the power sum basis. I describe how the elements multiply, how they co-multiply, there's a co-product. And then there's an internal product, and that internal product corresponds to what's going on in representation theory as well. So there are 3 operations on symmetric functions that we're going to try and keep track of. And so but there are 3 bases that I want to concentrate on this talk: the power sum basis, the homogeneous basis, or sometimes called the complete basis, and the Schur function basis. And I give, so the power sums, they are the monomials in these variables P1, P2, P3, and so on. The homogeneous elements can be written as a polynomial in the power sums, and the Schur functions can be written as a polynomial in the power sums. And the coefficients are actually something that's occurring in representation theory. And the reason why the Schur functions are important is because they encode characters. So I told you that the takeaway message of what I needed to know about representation theory is that the representation theory of GLN and the symmetric group are indexed by partitions, and those and I need to know the character values in order to understand the representations, the irreducible representations. So the Schur functions encode characters. In the case of the general linear group, they encode the characters by evaluations of the symmetric functions themselves. So if I put the variables back in, I have variables x1 through xn, and I have an element of my general linear group, and I substitute in the values of the x1 through xn, the eigenvalues of my element of GLN, then the S lambda of the eigenvalue are the GLN character values. And the symmetric group characters.
Can I ask a question, please?
Yeah.
In the previous slide, the Hopf algebra in terms of the power sum functions.
Mm-hmm.
So the algebra structure is the usual algebra structure, or there's some unexplained notation here. What is that lambda? Some funny plus mu?
Yeah, this is the normal.
And there was also
yeah. So the algebra structure here is multiplication of monomials. So if I have the monomial p lambda and I multiply it by the monomial p mu, because I'm thinking of these p mu and p lambda are products of these p's, then the result is a monomial again, indexed by another partition. And this partition, you're right, I did not explain the notation here. It's the usual product on variables. And so what do I have to do? If I have a partition lambda indexing one monomial and I have a partition mu indexing another monomial, then the operation needs to be, well, I take the parts of the partition and concatenate them and then resort them so that it becomes another partition. So that's this operation here is to concatenate and resort.
Yeah.
And then this operation here, well, I also did not explain what the z mu is, but it's just a coefficient. The order of this stabilizer of the action of the symmetric group on the on itself by conjugation for an element of it's a long. I'm not going to be able to state it very succinctly in this, but it's easy to calculate. It's just a number.
Thank you.
So there are two algebra structures. The one is the regular algebra, and then this one is it called an internal product. So Schur functions also encode the symmetric group characters, because if you look at the change of basis between the power sums and the Schur functions, the coefficients in front of the Schur function is a symmetric group character value. And this symmetric group character value, it's indexed by a partition lambda for the irreducible, for which irreducible you're talking about. And the mu is the cycle type of the element of the symmetric group. So every element of the symmetric group has a cycle type, which is a partition. It's like if I read it in terms as a product of disjoint cycles, what is the partition consisting of the sizes of those cycles? And so I evaluate the character at a partition at a permutation of cycle type mu, and that's the character value that occurs as the coefficient, as the transition from p mu to s lambda. But there's a second way in which Schur functions encode the...
Sorry, I have another question there.
Mm-hmm.
What is k? So in this formula that you have, p mu.
P mu is going to be a partition of k.
That's...
P mu is a partition
Oh,
of k, and
mu
lambda is a partition of k.
Okay, mu is a partition of k, you mean? Okay.
Yeah. Mu is a partition of k. Yeah, mu, P mu is of degree k. Thank you.
Yeah, thanks.
So there's a second way in which Schur functions encode the characters of the symmetric group, and that if chi is a character of the symmetric group, so it's the character of some symmetric group representation, then there's a map which we call the Frobenius map, which takes that character and maps it into the ring of symmetric functions. And this Frobenius map, it takes the character values and uses them as the coefficients in front of a power sum. And if you take an irreducible character of the symmetric group, then its Frobenius image is going to be the Schur function. And the reason why those three operations that I introduced for the symmetric functions are important is because I introduced product, coproduct, and the inner product on the symmetric functions, and those correspond to induction, restriction, and tensor in the representation ring of the symmetric. And I said one of the bullet points of the my summary of representation theory of symmetric group and general linear group is that of Schur-Weil duality. And this is where the n and the k interact. So I start, the general linear group is indexed by a positive integer n, because the general linear group is acting on a vector space V, which is of dimension n. And the action of this general linear group is A acting on a basis element Vi is Aij Vj. So it's the sum from j equals 1 to n of Aij Vj. And then I'm going to act this general linear group not just on V, but I'm going to act it on V tensor K. Right? And at the same time, I have an action of the symmetric group also on V tensor K. And the symmetric group acts on the K tensors by permuting the entries in the tensors. So this is, so if you express it as a sum of tensors, then it acts on one particular tensor by permuting the entries. And the Schur-Weil duality is that these two actions commute, and they are the largest space of actions that commute with each other. So V tensor K is a module. It has an action both of the general linear group and of the symmetric group at the same time. And this Schur-Weil duality being in existence says that this particular module will decompose as a direct sum of tensors. And it says that also that the the general linear group and the symmetric group will have the same index set for their irreducibles. And then this decomposition occurs, and the irreducibles occur with multiplicity 1. So the W lambda tensor W lambda of GLN, W lambda of SK occur with multiplicity 1. And this multiplicity of tensors of irreducibles of one of these groups is the same as the multiplicity and the restriction of the irreducibles in the other group. So this is the statement that they are super closely related, that the general linear group and the symmetric group actions are closely related, is that the multiplicities in the tensors of one is equal to the multiplicities in the restriction of the other. Well, the basic representation theory of the symmetric group and general linear group was developed over the beginning of the 20th century. But there are three unsolved problems that I think that we would like to understand from a perspective of combinatorial representation theory. Those of tensor, restriction, and plethism. That is, tensor, we really don't understand how to decompose the tensor of a symmetric group representation with another irreducible symmetric group representation in terms of symmetric group representations on the level of combinatorics that we would hope to have. We seem to understand this for many other groups, but for some reason there seems to be a block with respect to understanding this tensor problem from combinatorial representation theory. Another problem that we don't understand from combinatorial representation theory is how to restrict a GLN irreducible to an SN irreducible. So the symmetric group of permutation matrices sits inside of the GLN of all invertible matrices. So if you restrict from this larger group to a smaller group, then this irreducible will decompose into the symmetric group irreducibles. And we would like to understand how that happens. We have a formula that comes from characters. We can write down what the character is. We can expand it in the basis in symmetric functions, and there's a lot of linear algebra that goes on behind it. But the end result of that computation is mysterious to us on the level of combinatorics. We know that the numbers are positive. We just don't have a clear explanation of how they become positive and what they're counting. And then there's a third problem here that I'm going to skip over, but it's behind these two problems simultaneously. But I believe that plethism is closely related to understanding the tensor problem and the restriction problem, that we also must understand the plethism problem. But it's one that's left open, and I think it's because that our tools for symmetric functions and combinatorics are still lacking, that we can't explain these on the level of representations. But there was a gap in the representation theory of the symmetric group as the symmetric group sits inside of GLN. And that gap started to be filled in the 1990s that said this Schur-Weil duality between the general linear group And the symmetric group existed since Schur's thesis in 1905. But if you also act on the same side, the general linear group, you instead act by the symmetric group Sn as permutation matrices. Now we're not acting on the positions of the tensors. Now we're acting on my symmetric group elements, sigma and Sn, acts on the vectors, acts on the vector space V itself by sigma of Vi goes to V of sigma I. And then if we tensor this, this vector space together K times again, and we ask what is it that is Schur-Weil dual to this symmetric group action, this was answered in the 1990s by Martin and later by Jones, where they said the thing which is Schur-Weil dual to the symmetric group action is the partition algebra. And so once again, we have a decomposition of V tensor K as a direct sum of modules with multiplicity 1 of but these modules are tensors of an irreducible Sn module and an irreducible partition algebra module. And this duality relates the multiplicity of the tensors of the irreducibles of one of these two group, well, the group of the symmetric group and the restriction of the partition algebra. So, like I said, the tensor of the symmetric group modules is a problem that's left unsolved as far as combinatorics goes. And so I'm saying that that is encoded in the restriction of irreducibles in the partition algebra. So now we need to build up the tools. So this is relatively new. It's only 30 years old. So compared to the rest of representation theory, it's on the newish scale. And so now we're in a position where we want to ask, does there exist a basis of the symmetric functions that takes the place of the Schur functions in this setup? What are the characters of my Schur-Weil duality? What are the characters of my irreducible symmetric group modules? That is, I'm looking for characters of the symmetric group such that they're symmetric functions that if I evaluate them at the eigenvalues of a permutation inside of GLN. So the eigenvalues are dependent only on the cycle type of sigma. And if I take those eigenvalues and I plug them into my symmetric function, I want to get symmetric group characters. And the right way of thinking about this is that you need to make this extra long row n and consider it with n. This is independent of n because, again, I'm throwing away the variables. And then on the other side, I want to know what are the transition matrices between the power sums and this new basis, because the coefficients there are going to be the characters of the partition algebra. And so those were also studied in the beginning of the 90s by Halvorsen. He said, here's how you calculate the characters of the partition algebra. So he described what his partition algebra elements were that were characteristic of these are the characteristic classes of the partition algebra. There's one for every partition of mu of size less than or equal to n. And he says, well, if I take my every single basis element of the partition algebra is conjugate to one of these elements, and then if I evaluate the characters at those elements, I get the values. So if I use this as a generating function here, these coefficients are appearing. And then, so Rosa Orellana contacted me probably in the mid, like, I think it was like 2013, 14. And she says, does this basis exist? And I said, at first I said, no, I don't think so. And then I said, oh, actually, if you define this S lambda tilde to be the inverse Frobenius image of the Schur function as n goes to infinity, then you can calculate them. So we had a definition which would allow us to calculate these symmetric functions, but we had nothing as far. This was a terrible definition for anything else, because you really can't prove anything when you have this limit as n goes to infinity. So you have to assume that n is big enough. So I can calculate them in the computer, but it's not a good definition. It's not a definition that works. So we kept coming back to this problem and coming back to it and coming back to it. And eventually we were able to come up with a definition which we felt like, oh, now I can actually calculate these. I can understand them to the point where I could program this into the computer, and I could explain to somebody, this is how you define these symmetric functions. And we came up with not just one. I mean, eventually we kind of needed more than one definition. Just as there's more than one definition for the Schur function, there are many definitions for this class of symmetric functions. What's different about these, though, is that they are not homogeneous degree. So the S tilde lambdas are of degree, they have a top component degree, and then they have things which are of lower degree. And the most direct way of defining them is this expansion in terms of power sum basis. But the power sum basis that I'm defining here, this bold P, is not the P that you saw before. Instead, this bold P is broken up into smaller partitions. There's a little bit of notation which is not defined here, but just say there is a power sum expansion of these elements, and this power sum expansion is given by the elements off to the right. This isn't my favorite definition, but it is the most direct way of defining them. I think one of my favorite definitions is the one up at the top, is that these S tilde lambda are the basis which are, they satisfy some initial conditions, but otherwise they are the orthonormal basis with respect to a scalar product. And the scalar product is very much the scalar product that you see in representation theory. And then you can calculate them using Gram-Schmidt orthonormalization. But even that isn't very practical. It's not the one that you normally use even for the Schur functions. But it makes it clear that this basis is very fundamental. It's saying that, hey, the basis which is orthonormal with respect to some very natural scalar product is a super useful tool in the theory of symmetric functions to represent characters.
Mike, I'm not sure what you mean by the basis that is orthonormal with respect to the, don't you need another condition about maybe the highest degree term or something?
Yeah, you do need a highest degree term or an ordering on the basis elements, but say use the same sort of technique that you use in order to define the Schur functions. When
So
I
would,
say plus Gram-Schmidt orthonormalization, I mean in the same way that I do for Schur functions, that you say, okay, the base case is you either start with a row or a column, and then you say, well, I'm going to take my next one and orthonormalize it with respect to. So yes, there is a missing condition in this statement here.
So for Gram-Schmidt, you'd usually start with a basis that's not orthonormal, and then you transform it to an orthonormal basis.
Right.
And you
And I
could
would start with that, except I wouldn't even start with, yeah, I guess I would start with a Schur basis.
which is not orthonormal with respect to this other inner product. Okay.
Yeah.
All right, thanks.
Yeah, so another definition which is practical, but it's not ideal, is the transition matrix between the power sums and this S tilde basis are the characters of the partition algebra. But then you would, if you use that as your definition, then you'd have to go to this paper by Halvorsen to understand what those coefficients are. The ones that actually got us bootstrapped off of everything else, and that we started to understand what these were, was we said, oh, the transition coefficients between the homogeneous basis and this this irreducible character basis are the multiset tableaux whose content is mu. So if MST is the multiset tableau of content mu, those are similar to what I did before. I make a column strict tableau, except now I put as my entries multisets. And there's a little bit more condition, is that I need enough blank cells in order to make this, the number of blank cells must be longer than the second row and above in order for this to make sense. But if you take that as your definition of multiset tableau, and you pick some ordering on the multisets so that you can define what it means to be weakly increasing and strictly increasing in the columns, then the coefficient of the irreducible character basis in my H mu is equal to the number of multiset tableau of content mu and of shape lambda in the second row and above. So this bar here is another piece of information that another notation that I've left off, is that bar says remove the first row. What's practical about this is that there are ways of expanding any symmetric function f. So if I have f is a symmetric function, I can expand it in this irreducible character basis, either by using my scalar product.
Hello, Mike. Can
Yes.
I ask you a question?
Yeah.
So in the previous slide, you took n to be equal to 16.
1, 2, 3, 4, 5,
Means
6, 7.
your definition must be like kind of, the partition must be n minus mod lambda comma lambda, that kind of thing.
Well, so my n is actually any n which is is bigger than twice the size of the shape above the first row.
Yeah.
Yeah, so I guess I take 1, 2, 3, 4, 5, 6, 7, 8. I need it to be 16 because it has to give me a lot of blank cells in there.
Yeah. Okay.
There are little tricks about the combinatorics of the coefficients here that you only get into if you start delving deep into it, but I
And the
didn't need to.
order and the order of the multiset, you can take anything, means any total order is perfect for this to define this multiset tableau here, or
Yes, you fix one because column strict tableau, you can switch the number of 1s and 2s, the number of 3s and 4s, the number of 5s and 6s. So it really says that basically you can permute the content in any way you want. So it says really any order will work, but you have to fix an order just for consistency.
okay, thanks.
So the reason why we were interested in this, and I mean, even when Rosa first approached me, the reason why I had been interested in this at all is to get a hold of the restriction problem, is that I want to understand what this what are the multiplicities when I restrict a GLN module from GLN to the symmetric group sitting inside of GLN. So if you have an irreducible GLN module, if I restrict to a smaller group, the irreducible will decompose into irreducible SN modules, and the multiplicities R lambda mu happen to be the coefficients of S mu into S lambda tilde. And what Rosa was interested in were these multiplicities when you multiply S lambda tilde times S mu tilde. And these are known as the Kronecker coefficients, but they are a subcase of the tensor problem. If you want to know how an irreducible SN module indexed by n minus lambda comma lambda tensor and another irreducible indexed by n minus mu comma mu, how that decomposes into irreducibles, the multiplicities are these reduced Kronecker coefficients, G lambda bar, lambda mu nu, lambda mu gamma. And those are exactly the coefficients which occur in the product of this basis. And they're non-negative, and we want to understand them in terms of combinatorics. So I'd like to be able to say, I can give you a combinatorial interpretation for those coefficients because of this basis. I can't. I can give you a combinatorial interpretation for some of them, but I can't give you a combinatorial interpretation for all of them. I'm seeing some information. So is there a nice Cauchy formula for your tilde version of the Schur functions? I think the answer is, I don't have one. That's a very good question, and believe me, I've searched. But the dual bases have to be very complex because one is Schur functions plus terms lower, and then the dual bases have to be Schur functions plus terms larger. And so I don't quite know how to make a Cauchy kernel out of that.
How about for your power symmetric your version of the power symmetric functions? Is there some
Same problem happens.
same problem?
Is that those are power sums plus terms lower, and so they have to be power sums plus terms larger, and I don't know how to put them together in a Cauchy kernel that makes it nice. It might be a truncated Cauchy kernel, but I'd have to I've been thinking about it, but I don't have an answer to that. So I can't give you a combinatorial interpretation for these G lambda mu gamma, but I can give you a combinatorial interpretation for G bar nu lambda A1, A2 up to AL. So I can do repeated Peary rule, but I cannot do all of the coefficients as I would want. This, I think, is a big step closer to understanding the reduced Kronecker coefficients, because the Littlewood-Richardson rule comes from doing a Schur function times a mu1 times a mu2 times a mu r. So it's exactly the same type of rule. And then this product contains one term, which is lattice, and then the other stuff, which is not lattice, and then a combinatorial interpretation for S lambda slash times S mu is equal to the tableaux, which are lattice. And so I'm speeding through these last couple of slides, but because I want to kind of get to the main idea, I have a vague conjecture that goes on that there should be a notion of lattice in this setting, such that if I add this additional condition on my tableau, that this is a combinatorial interpretation for G bar nu lambda mu, because it works in the case of the Littlewood-Richardson rule. So I'm working on it. We seem to have had a rule which worked up to, up to a certain degree, and then it starts to fail. So our notion of how to come up with this this rule at the moment is kind of blocked by the fact that the combinatorics of multiset tableau seems to be a level of complexity higher than that of column strip tableau. And so here's my takeaway message. The following concepts have developed about representation theory and combinatorics of the Littlewood-Richardson rule over nearly 80 plus years of mathematics. And I don't quite know how I'm counting 80 plus, but we developed the notion of a Peary rule and a repeated Peary rule, and the Robinson-Shenstedt-Knuth correspondence comes up in the 1970s. Lascaux and Schutzenberger invented the jeu de taquin and the plactic monoid, and developing the reading words and how to understand them as being lattice, this lattice condition on the Littlewood-Richardson rule. So I need to develop similar operations for set-valued tableau and multi-set valued tableau to arrive at a combinatorial Kronecker product rule. And I believe that that same rule, which will help me get the Kronecker product rule, will also get the restriction problem, and as a consequence, plethism, because plethism is very, very closely related to the restriction problem. So we have guides for developing this combinatorics, and those guides are the representation theory of the partition algebra, the multi-set partition algebra that some of you have worked on, the symmetric group character basis, and we need to develop others. So I'm encouraging people to work on this representation theory of the partition algebra and multi-set partition algebra and with respect to this basis, because I believe that we're just missing the very tools that we need in order to solve these open problems of representation theory and combinatorial representation theory. And so I'll end there. Thank you very much.
Well, thank you, Mike. I guess we can unmute our microphones and thank Mike here.
Thanks.
Can- yeah. So, are there questions? There are some questions.
I would like to ask. I would like to ask a question.
Yeah, go ahead.
Definition of the new symmetric basis as generating functions for a combinatorial object.
I'm having a hard time hearing you. Can you?
Do you have a definition of the new symmetric basis as a generating function for a combinatorial object?
No, that would be a big advance. You mean as a monomial expansion?
Right.
Yeah, understanding the monomial expansion or the Schur expansion would be really good, but it seems to be very hard, and it's very closely related to this restriction problem. So so Sami Asef and David Spires also looked at this basis, and they had shown that the scalar product this is the classical scalar product in symmetric functions. They showed that the coefficient of S mu and S lambda tilde alternates with sign as you go in degree. So the coefficient of S lambda in S lambda tilde is 1. And then as you go down in degree, they're negative, and you go down in degree positive, negative, positive, negative, positive. And we observed that, but we didn't really work on proving it. But Asef and Spires managed to show that it does this, it has this alternating property. Coming up with a monomial expansion seems to be harder.
But are those monomial, in the monomial expansion, why would the coefficients be non-negative? I mean, is that?
Well, because then the Schur functions expand non-negatively in the monomial basis. And so it's going to definitely have the exact same property, but actually coming up with the monomial expansion seems to be hard. And it might be related to other combinatorial representation theory problems.
Sorry, I've got a question you might have already answered to me. So what's the highest degree part of this tilde mu, tilde lambda?
It's S lambda.
Ah,
Yeah,
so it's
S,
a lower degrees versus funness.
Right. S tilde lambda is S lambda plus terms of lower degree.
Have you tried comparing it with other families like this, stable dual Grothendieck's, for example?
Yes. Because
Nothing
again,
much, right?
multi-tableau, there's a different condition on the multi-set tableau that occur in Grothendieck and dual Grothendieck's. It doesn't exist in ours. Basically, we're saying they're column strict with multi-set entries.
But the functions don't look similar either, right? Not just the definitions.
Well, they do in the sense that that they're Schur function plus lower degree, and then they're dual. Well, actually, the dual Grothendieck's are Schur functions plus lower degree, right? And
yes.
then the Grothendieck's are Schur functions plus things higher. And this has the very same property, but I have not been able to compare the coefficients in any meaningful way.
Also, one more thing. In the very first formula that motivated the definition of your tildes, the one where you apply it to psi mu and you get this character value, can you scroll back?
Yeah. There.
Okay, so you add a row with size n minus size of lambda. What if n is smaller? What if that is smaller than lambda 1? Is it understood to be only work for n big enough, or can I even say n equals size of lambda and that's just lambda?
You can do it for any n. Well, I guess if n is well, I guess you need to interpret it with the with the relation, if the row is too small, then you need to have the positive and negative
Dot action.
row switching. Think of it as a Jacobi-Trudy determinant.
I see. I see. So if n equals the size of lambda, I just get lambda there.
Yeah.
Perfect.
Wait, if you get,
Or no?
if n is equal to the size of lambda, then you get 0, and then the parts of the partition lambda above. And then
so
you
I
have
need
to swap it in, and so it removes a
one from each, right?
a slinky on the right-hand side of the partition.
I see. I see.
So are there any more questions? Mike, I actually was a bit confused about one of your slides.
Sure.
I think you'd said that the multiplicity of tensor of irreducibles are equal to the, I think it's slide just before this, but when you talked about partition algebra, Schur duality. Yeah.
Yes.
So can you just explain what this means? Multiplicity of tensor of irreducibles on one is equal to restriction of irreducibles on the other.
Okay. So in the case of the Schur duality for symmetric group and partition algebra, there's a result of Bowman, de Vischer, and Orellana, where it says that the tensor, so the multiplicity of a tensor of a symmetric group module is the Kronecker coefficient.
Right.
And on the other side, it says that the restriction of a partition algebra irreducible has the multiplicity of the Kronecker coefficient. So if you restrict an irreducible partition algebra module from p k plus L of n, I kind of wish I could write this out in
pk plus L to pk cross pl, or?
Yeah, exactly. I want to say, let me see if I can write it. P k plus L of n to pk of n cross p L of n. So if you restrict an irreducible from this algebra to this algebra, and you ask what is the multiplicity of an irreducible of this algebra in here, it's going to be the Kronecker product again.
Okay. Okay, okay. Okay, great. Thanks. So are there any more questions? Well,
yeah. Can I ask a question? Hey,
Yeah,
Mike. Yeah, so I was wondering, you kind of you mentioned like plethism kind of in passing a lot. And I mean, I know from thinking about this stuff also how these kind of multiset tableaux show up in thinking about the plethism problem. I was just wondering if you have any more like, you know, sort of a concrete formula relating your basis kind of directly to plethism coefficients. Beyond it just being sort of, we know they're vaguely related because the same combinatorics is showing up.
Well, so this is the very specific one, but this is Littlewood's identity in disguise.
I see.
And that it says, hey, if you want to expand any symmetric function in the irreducible character basis, the coefficients are, you kind of need to be able to compute plethism in order to compute these. Now, one way of computing that plethism is to compute this scalar product. But that's Littlewood's theorem that says, hey, if you want to compute this scalar product, then you can compute it using this plethism. Again, we're stuck on the combinatorial level. We really want, this is a positive number a lot of the times. For various f, this is a positive number. And we know how to compute this if f happens to be h mu, because then it's multiset tableau. And if f happens to be a Schur function, then we don't know how to compute this. And, well, at least on the level of combinatorics, right? We know how to compute it on the level of symmetric functions, but and so ideally, what I'm looking for is a combinatorial formula for the scalar product here of S lambda, or of S mu, and this plethism. And I can show you in terms of this basis where it comes up. If I want to get my hands on that, I have a tableau way of getting my hands on it, on getting h mu. Well, I guess this isn't exactly the slide that I would want to explain it with, but again, I can explain it in terms of tableau when it's h mu, but I can't quite explain it in terms of tableau when it's s mu. And that's the problem here that's encoded in this I believe a lattice condition on these tableaux exists, which explains what that coefficient should be. Again, we don't have the techniques yet. They're not there. We're close. I really think that somebody smart is going to come up with the right techniques of how to interpret multiset tableau in the near future.
SI interpretation, multiset tableau, for instance.
Sorry, what?
An interpretation of, multiset tableau in terms of what are they called? SI modules.
SI modules.
FI perhaps? Or?
Oh,
FI modules, I meant to say, yeah.
I know the term, but I'm not familiar with it enough to comment.
I don't know one off the top of my head, and I do know that stuff pretty well. I mean, they're definitely related. These problems, kind of FI modules, deal with kind of similar kind of stability with the symmetric group representations that we're seeing here, where you have this kind of long first row that you're looking at kind of the stable behavior of these coefficients. And so I think these types of questions show up in that setting a lot as well, but I don't know that there's like a better way of expressing them in that language.
We do have a result about that. For the analog of FI modules for representations of GLN are strict polynomial functors. And it's possible to define a restriction functor from the category of strict polynomial functors to FI modules, which upon evaluation gives this restriction from GLN to SN. So in that sense, you can work with FI modules. I mean, these are stable, these restriction coefficients. So.
Yeah, so the reference is given on the chat.
I have a really speculative question, Mike. We have these three problems, right? The Kronecker, the plethism, and the restriction. And always the game is to find some sort of non-negative formula for the expansions. Do you think solving any one of these would solve the other two?
Yes.
Is there any? Is that a fact? I mean, is that?
I say it without hesitation, and I have no evidence for that.
Oh, okay. Okay, so it's kind of a feeling that I keep getting, but I don't know if there's a statement. There's stuff in complexity theory, I think, which says that if you can solve one of these fast, at least between plethism and tensor, I think there are results. I'm not sure how restriction fits into that.
Well, like I have a context for which I have these multiset tableaux. They're relatively complex, but I feel like if I define a lattice condition in the natural way, it explains the tensor coefficients and the restriction coefficients at the same time. But I don't have it for everything. I can't explain all of them. So I think that we don't quite have the combinatorics there. I think it's close. I don't know if I can get it. I'm hoping somebody can. I'm encouraging everybody to look at these problems because I find them absolutely fascinating, but I realized that I found them absolutely fascinating when I started mathematics 30 years ago.
Yeah.
That nothing's changed. Nothing has changed, is that we are still in the same spot.
Yeah.
So can I ask another question?
Yeah.
So for the restriction problem, that Littlewood rule you said, so there you have to expand the plagism problem like S lambda of 1 plus H1 plus H2 in terms of the Schur function, right? S mu. And the
Right, you're talking
yeah,
about
here.
this one, right?
Not
Or
here.
maybe not, because I didn't go over this part, but
Not here. And before that, Littlewood formula of
oh, this?
No.
no, S lambda plagism of 1 plus H1 plus H2.
Oh, okay, that one.
This one, yeah, when
Yeah.
F equal to S mu. So your restriction coefficient is just the change of basis of these two symmetric function. S lambda of 1 plus H1 plus H2, that thing, and the Schur function S mu, right?
Yeah.
Yeah. So do you think that having a representation as a GLN representation whose character is this plathism, S lambda of 1 plus H1 plus H2, is a good tool to attack this problem? Suppose you have a module, GLN module, whose character is this plathism, S lambda of 1 plus H1 plus these two.
It's a GLN module? Yeah, I mean, shouldn't that be the...
No, I'm not doing for this n minus mod lambda. I fixed that size of lambda. So suppose lambda is a partition of n, and if I look on just S lambda plathism with 1 plus H1 plus H2 that thing.
Yeah.
And I want to find a module. Yeah. So we have one module for that. So having that module whose character is this plathism, is that a good tool to count that restriction coefficient? Do you have any view on that?
Possibly. I mean, I hadn't thought of it that way, because normally this would be this side would be the symmetric group character, I think. Not the GLN character.
Yeah, that's right.
So that's an interesting way of looking at it. I don't know if it would help, but it certainly can't hurt. Because then you would want to decompose that GLN module into irreducible GLN.
Yeah.
I mean, you may have reduced the problem from one hard problem to another hard problem. That's all we've been able to do so far.
That's
120 years or more of
that's called progress in this area. So, are there any more questions? Okay, I guess, well, that was a really nice talk, Mike. We really enjoyed it. And as you said, some of us are working on the restriction problem. So there's a lot of thought here. And,
I did not mean to do that. I really like some of the work you guys have been doing. It totally fascinates me, and we're thinking about the same questions, the same problems, and I really hope you can solve them, because so far I haven't been able to.
So that last bit that you talked about with the Kronecker coefficients, that's not published yet, is it?
Yeah, it is. So this is in JCTA.
Oh, okay.
Where we give, so I think it's called products of symmetric group characters or symmetric, like our original paper on the symmetric group characters has not been published. And I went to track it down recently, and the editor said, oh yeah, the reviewer said he can't do it for health reasons, and so you need to find it.
It's been in review. It's been, yeah.
It's only been 4 years in the review process.
Okay. Okay, that makes us all feel better about our papers.
Yeah. Our last 3 paper, actually, we cited your paper in this thing. So it's good. Then our thing is not yet published. It will take more time then.
It's hard to read these things. And so I understand it takes a long time. And then there are the holdups of life. And really, I've gotten no reviewing done since we shut down. I mean, as much as I would have liked to, it's just, that's one thing that's moving slowly. I hope to get back, now that I'm finished with classes, I'm gonna move forward on some of the ones I have to do. But so I understand why my papers are not getting reviewed now, but it's slow in general. Bye, Janine. It's nice meeting you.
I have to disappear. Nice to see you.
Nice to meet you too.
Okay, yeah, so thank you, Mike, and thanks everybody for coming here. We'll have another talk next week at the same time by Nate Harmon. Keep an eye on the website for updates. Bye, everybody.
Nate, is that going to be on the same sort of thing?
Well, that's why I've been debating what to talk about, but I feel a little inspired after watching this, so it might be.
I feel like we should have a worldwide meeting on this sort of topic and see where people are, because I really think that progress can be made.
I very much agree. I think this problem's waiting to be toppled.
Yeah, let's do it. We don't even need any money if it's going to be on Zoom.
Bye.
Okay, bye.
Yeah, we'll just figure out a time when we're all relatively free, and we'll just organize something.
Yeah, I think it's a good idea, but I don't have any concrete, actionable math to bring to it yet. But I mean, I guess this is concrete, actionable.
No,
Find me lattice.
Yeah, no. So we'd like to see some of these things in more detail and so on. So maybe it's not a bad idea.
Okay.
Okay, so I guess we'll yeah. So I guess we'll end this for now.